When we're calculating probability, it's important that we see the difference between dependent and independent events. It definitely changes the calculations. However, when we have incredibly large data sets and we are only looking at a sample that is no more than 5% of the size of the population, we can treat the selections as being independent, even if they're not, and even if the selections are made without replacement. In other words, when our numbers are so large and we have such a small sample size in comparison, we can simplify our workload and calculate probability as if the events are independent. Let's take a look at an example to help us understand this concept. Assume that on a given day in a fruit packing shed, there are 2 million pieces of fruit to be packaged, of which 1,000 have some sort of defect. If 10,000 pieces of fruit are randomly selected, find the probability that they are all good. Let's think about this one piece of fruit at a time. If we pull one piece of fruit out of the 2 million at random, what's the probability that it's a good one? That is, doesn't have a defect. If there's 2 million pieces of fruit and 1,000 of them are not good, that means that 1,999,000 of them are good. So the probability that the first piece of fruit chosen at random is good is 1,999,000 divided by 2 million. Now we pull our second piece of fruit. Since that first piece of fruit has already been pulled, there are now 1,999,999 to choose from. And if one good one has already been pulled, then there are 1,998,999 good ones left. And now we pull the third piece of fruit. With 2 pieces of fruit already pulled, there's 1,999,998 to choose from. And if 2 good ones have already been pulled, there's 1,998,998 good ones left to choose from. And we would need to repeat this process 10,000 times in order to calculate this probability properly, with each of these being dependent events. This is where the 5% guideline for cumbersome calculations really does come in handy. We have a large population, 2 million pieces of fruit. We are selecting 10,000 of them. 10,000 out of 2 million is equal to 0.005, much less than the 5% guideline. That means that we can treat each of these events as independent rather than dependent. Treating these independently, we can find that the probability of pulling one good piece of fruit is equal to 1,999,000 divided by 2 million, or 0.9995. And if we consider this to be the probability for each piece of fruit pulled, we would need to multiply 0.9995 by itself 10,000 times, which is simply 0.9995 raised to the exponent of 10,000. And putting that into our calculator, we find that the probability of pulling 10,000 pieces of good fruit is 0.0067. Treating these events as dependent, the calculations would have taken us a very long time. But by treating them as independent, we were able to do the calculations much quicker. Now that we know that the probability of them all being good is equal to 0.0067, let's calculate the probability that this batch of 10,000 pieces of fruit will not be perfect. That is, at least one piece of fruit is bad. Having at least one piece of fruit bad is the opposite of having every single one of them be good. So we can calculate the probability of at least one being bad, that is, they're not all good, by finding 1 minus the probability that they are all good. That's 1 minus 0.0067, or 0.9933. In other words, if you're drawing a sample of 10,000 pieces of fruit, the probability that at least one of them will have a defect is 99.33%.